Hello, my name is Austin Chadwick from the Jameel Observatory CruiseNet team. I'm a postdoctoral scholar at the Columbia Climate School Lamont Doherty Earth Observatory with over 10 years of research on how coastal river systems evolve and respond to climate change. I work with PI Michael Steckler, who has over 20 years of research and expertise on the Ganges-Brahmaputra Delta. Today, I'll be talking to you about our ongoing work on adaptation to relative sea level rise and flooding in coastal Bangladesh in the 21st century. I'll start with an example. On May 26th this year, Cyclone Remal made landfall in southwest Bangladesh. Storm surges of up to 3 meters breached levees, flooding, and contaminating farmlands with salt water, as shown here. Zooming out onto the delta as a whole, you can see Rampal and Cyclone Remal. Almost 1 million people were forced to temporarily evacuate their homes. Almost half of all standing crops were damaged, and more than 500 million was lost in terms of assets and infrastructure, mostly in the affected areas highlighted in red, mapped by Brock. And I'll ask the question, to what extent can we predict and defend against hazards like Cyclone Remal in the future with climate change? Well, to first order, we can use passive flood mapping, or the bathtub approach it's called, to estimate the potential flood depth or the levee height needed to defend against it. What I mean by this is if we take a profile from A to A prime, shown in our schematic on the right, we can imagine raising the sea level during the storm surge and asking the question, what is the levee height on the left that's going to be needed to defend against flooding at that point? We can express this in terms of a mathematical equation shown here, and plugging in up-to-date values from the storm surge, we can create a map of the defense height that's needed. And I'll do that on the left here in overlay. And you can see from this color-coded map that these defense heights correspond pretty well with the effective areas. But this is not enough for the future, where defense against storm surge, sea level rise, and also land subsidence will require levee enhancement and/or sediment deposition by rivers. And you can see this on the right in our updated schematic. If we plug in values for these for the next century, we can do a pretty good job, but the problem is this subsidence term. So this is how the land is sinking over time, which is notoriously difficult to understand and constrain for the future. And that's where we come in. Our field efforts show how land subsidence varies over time with sediment deposition, groundwater levels, and the surface ecology, all of which are sensitive to climate change. You can see here our array of subsidence stations throughout Bangladesh, where we use a combination of methods, including GPS, broad surface elevation tables, tide gauges, augering and coring, as well as the investigation of historic sites to characterize this land subsidence. This gives us a broad picture of how the dynamics of this landscape evolve over time with many different methods. We couple these modern measurements with a predictive model for subsidence in the future. This is based on fundamental principles of sediment mass conservation, effective stress, groundwater flow, and material properties of porosity of the sediments. We incorporate the surface ecology, the sediment deposition, and these groundwater levels, which are all sensitive to climate change, in order to predict how the subsidence rate is going to vary as a function of depth at a given location. And this can be compared directly to our subsidence measurements with different methods through depth integration. This model can help inform where and when levee enhancement, sediment diversions, or other adaptations will be needed in the coming decades. Here I'm showing you our map from earlier, where now I will plug in our subsidence model into that H subterm to update our map to ask the question, what will happen if we have a cyclone Remal of like event in 2100? So here is 2024, and we'll now update to 2100. And you can see from this map that by 2100, defense against a cyclone like Remal will require 3 to 5 meters of sediment and/or levees to protect these lands, with hotspots above ancient river courses. In terms of these courses, I'll now overlay this map of the sediment thickness in the ancient courses of the Ganges and the Brahmaputra rivers during the last ice age, and showing you how they correspond with these warm spots on this map. This is showing us how the geologic past of this area holds keys to the future of resilience against climate change. With these findings and more, we are building climate impact assessments in connection with the broader Jamila Observatory CruiseNet team. Thank you very much.